As we were saying last time, the probability amplitude of being +1 is the inner product of U and A. The probability amplitude of being -1 or spin down is inner product of D and A. The probability itself, it's the square of those amplitudes. So probability that we have an upspin is this product right here. The probability that we have a downspin is this product right here. Also, just to remind you, U and D, the inner product of those two basis vectors, is always 0. They're all orthogonal, in fact, orthonormal with one another. That is to say, if I prepare a spin in the up state, there's 0 probability that it will be detected in the down state, and vice versa. Notice, just to remind you, this is a spin space. We're not in configuration space. We're not really talking about literally up and down and left and right. This is a spin space, so please don't assign anything more physical to it than that. Also, to sort of complete the thought, if I add alpha star U alpha plus alpha star D alpha D, the sum must equal 1. Why? It has to be either spin up or spin down in any case. Which, of course, then means A with inner product A is also equal to 1. Okay, so we've done that all along the z-axis. I'm going to come over to this side of the board, and we're going to start to do it again with the x-axis. Let's see what develops. Along the x-axis, let's try representing each spin state in terms of basis vectors R and L. If apparatus A initially prepares in the R state, and then we rotate to measure sigma sub z, there should be equal probabilities that you'll get spin up or spin down. That is to say, equal probability that you'll get U or D. So the probability then, of course, is going to be equal to 1/2 in both cases. Probability for up is 1/2, probability for down is 1/2. If I were to rotate back to the z-axis. That being the case, I can write a vector R, a ket R, as 1 over the square root of 2u plus 1 over the square root of 2 times ket d. By the same token, I can look at the ket L, and I can write that. Probability of being up again is the same as the probability of being down when I measure the spin along the z-axis. So another equation that would work would be 1/2 u minus 1 over radical 2d. So if you're wondering about the square root of 2, remember that we want to keep these orthonormal. And so that square root of 2 is going to be important. Now, here's the truth. There are going to be some ambiguities in R and L, because if you notice, we could multiply either R or L by any complex number and still get the same answer. So for example, we call this a phase ambiguity. So in other words, if I do the following, suppose I let z, some complex number, equal e to the I theta. No matter what, if I take R star R or L star L, bra R, bra L, ket R, ket L. Notice I'm going to get the same result that alpha u star alpha u plus alpha d star alpha d is still going to be equal to 1. So we can only know this up to a phase factor. But then again, the phase itself will have no effect at all. You're still going to get the same answer. Same idea. Let's try this along the y-axis. So we've done it along the x-axis. Same idea. Along the y-axis, I know that I-O are equal to 0. So if the spin is out, it's definitely not in, and vice versa. We have some added constraints on I and O. It has to be that if I measure U after measuring O, I have a 1/2. If I prepare everything in the O state, the chances of getting a spin up when I go to the Z component is 1/2, and the same thing is going to happen for the D component. That's 1/2 as well. Similarly, for if I prepare everything in the ith state along the y-axis and I rotate to the z-axis, the probability amplitude is still 1/2 for getting up, and still 1/2 for getting a downspin. So I can write my I ket as 1/2 or 1 over square root of 2 times U plus I over square root of 2 D. I can write my O ket as 1 over square root of 2 U minus I over square root of 2 D. And these will be sufficient descriptions for those kets. We can also represent spin states as column vectors. So I can write U as 1, 0. I can write D as 0, 1. And from all of these, I can calculate ket I, ket O, ket R, and ket L from all these considerations. That brings us to the introduction of another concept in quantum mechanics and the linear algebra associated with quantum mechanics, and that is linear operators. States in quantum mechanics are mathematically described as vectors in a vector space, but physical observables in quantum mechanics are described by linear operators. By physical observable, you might just think of it as something that you measure. They're associated with a vector space, but they themselves are not state vectors, and operators are not state vectors. We can think of a linear operator as a machine. Think of a machine that has an input port. So maybe I put in a state vector like A into this machine, and then in my output port I have a vector that comes out, a state vector called B. And oftentimes we'll indicate the operator by a capital letter with a hat over it, a caret over it, where M is my operator. In the case of this machine, though, in order for it to be a linear operator, there's some criteria that have to be upheld. First of all, a linear operator, like this one, has to deliver a unique output for every vector in the vector space. So you can't have the same output for two vectors going in. It's got to be a unique output. Also, if we say M applied to ket A is equal to B, and if Z is a complex number, it must be that M times ZA is going to be equal to ZB. So it's linear in that respect as well. Moreover, if I operate on two vectors with M, that is to say M applied to ket A plus ket B, that's going to be the same as applying M to ket A and also applying M to ket B. So linear, it's a linear operator. And as I say, the important thing to remember about linear operators is they are the way that we represent physical processes. So, let's go back to matrix representations. We're going to talk about sort of the row and column orientations and how they depend upon the choice of basis vectors. So suppose I have an n-dimensional vector space I can choose n orthonormal basis vectors, and we'll call them J. And of course, corresponding raw vectors, J in this respect. If I want to write the operation M operating on ket A equals ket B in component form, I'll represent A by sum over J, alpha sub J, ket J. And I'll do the same for B. I'll write, so B will be equal to sum over J, beta sub J, ket J. It must be that I can write sum over J M operating on J is equal to alpha sub J, which will be equal to sum over J beta times ket J. So if I'm doing it in component form, it looks like that. Interesting thing happens when I take the component form and multiply both sides with a basis vector k. So I can do the following: sum over J k M J alpha sub J. That's going to be equal to sum over J beta sub J k J. Now, remember, this term will be 0 unless k is equal to j. In other words, kj is equal to Kronecker jk. So unless k equals j, it's 0. So the sum on the right-hand side collapses to just one term. It's just going to be beta sub j. let's define mkj as the product k mj. We call m sub kj the matrix element of M, and it's just a complex number. Furthermore, we can arrange the matrix elements in a square n by n matrix. So for example, suppose n equals 3. We can arrange our matrix elements in M as M11, M21, M31, M12, M13, M22, M23, M32, M33. So it looks like a real matrix. And so it's equivalent to write then some mkj times alpha sub j is equal to beta sub j. And it's just as equivalent to write it as this: alpha 1, alpha 2, alpha 3 equals, so this is MA, is equal to beta 1, beta 2, beta 3. So this is a matrix representation of this operator notation. Along with this, we've got some special kinds of operators to talk about, or conditions on operators. And for that, we're going to talk about eigenvectors and eigenvalues. If I have a linear operator acting on a vector, generally speaking, it's going to change the direction of that vector. But for some linear operators, there are certain vectors whose direction won't change by their action. Those are called eigenvectors. So what that means is that if I have an operator M acting on a particular vector lambda, it will not change the direction of the cat at all, and will be just equal to the product of a number times that cat, a constant. We call this number lambda an eigen or characteristic value. And of course, lambda is just, this other lambda inside the bracket is just a ket. So when we feed this particular eigenket eigenvector into the machine, into the operator M, we come out with the same ket multiplied by a number, by a constant. So those are very, very special kinds of operations. It's an operator that operates on a special kind of a ket that results in that same ket multiplied by a constant. Good example of that, suppose operator M is 1, 2, 2, 1. I know, or I will know, that a ket that would be an eigenket of that system would be the ket 1, 1, because notice, if I apply M to ket lambda, that's matrix multiplication, 1, 2, 2, 1 times 1, 1, and I get 3, 3, or 3 times 1, 1. So in this case, my eigenvalue, lambda, would be plus 3. Very nice. These special kinds of vectors, eigenvectors and eigenvalues, will turn out to be very, very important to us as we go further in quantum mechanics. Linear operators also act on bra vectors, so I can do the following. I can take some ket B and act on it to the left, such that maybe my bra vector can be written as beta 1 star, beta 2 star, beta 3 star as a row matrix. And what that means then is that this is going to be equal to beta 1 star, beta 2 star, beta 3 star times M11, M21, M31, etc., M33. Multiplying the matrix on the left-hand side. Note, if M applied to A is equal to B, it's not true that if I turn it around, operator M applied to bra A gives me bra B. Not true, because we have to be careful. Complex conjugation comes into play here. Well, let's examine complex conjugation in terms of operators. They're not just simply numbers, so we can't just take a complex conjugate, at least in that way. We have to be a bit careful.
Dr. Blose, we have 4 minutes left.
Let's look at it this way. If I write M A equals B, in component notation, I can write that as sum over I M J I alpha I is equal to beta sub j. The complex conjugate of this would be sum over I mji star alpha I star equals beta j star. So what we're going to use is this notation A, and for M we're going to use an M dagger. That dagger indicates a Hermitian conjugate. If I want to take a Hermitian conjugate of an operator, what I have to do, if I treat it as a matrix, I take the transpose of the matrix, we interchange rows and columns, and the complex conjugate of the members of the matrix. So in short, something like B times M would be written as, or I should say A times M would be written as alpha 1 star, alpha 2 star, alpha 3 star times M11 star, M12 star, M13 star, M22 star, M12 star, M23 M3 star M21 star M22, M23 star M31 star M32 star M33 star. So it's taking the complex conjugate of each element of the matrix and the transpose of the matrix. Remember transpose again, where I interchange rows and columns. So we can write the Hermitian conjugate of M is written as M transpose complex conjugate. That means that if M times A is equal to B, it means that M conjugate times Ra A is equal to Ra B. That is the correct expression. In most cases, quantum mechanical observables are always represented by linear Hermitian operators. In that case, when they're Hermitian, the operator itself is equal to its complex conjugate. We'll talk more about the properties of Hermitian matrices and Hermitian operators next time.